Hello all, welcome to the AI driven perception learning and mapping for drones course. This is the 7th tutorial for Math for AI. So in this particular tutorial, we'll actually look at a MATLAB demo for these two objectives. First is we'll try to go over the understanding of a convolution operation. Essentially this is either in a 2D space, which is essentially the convolution operation, and then its interpretation in the image space. Once we have done that, we would also quickly take a look into the example of transfer learning. So this is something which was covered in the lecture. However, we'll just try to take a quick example in MATLAB. And again, before we go into a deeper dive of MATLAB, we'll try to clear some basics out. However, the focus of MATLAB's demo is mostly on the interpretation. So we have a code and we are running the code, and yes, please, in case you are using MATLAB, yes, the syntax is important. However, if you are using Python, overall the focus is the interpretation. So if operate more on what is the intuition behind those operations, right? And we would after, I think maybe from the next tutorial, start with a detailed discussion about PyTorch, how PyTorch could be used and how these operations could be done. And there we would focus more on the syntax in detail. Right. So for all the MATLAB tutorials, the focus is more towards the understanding of the operation. But yes, in case you are planning to use MATLAB for deep learning operations, please do focus on the syntax as well. However, for this tutorials, we would try to focus more on the intuition and the operations we're trying to do. So much less focus on the syntax for now. Okay. So before we go into the demo for transfer learning and even the convolution operation, essentially when we are training neural networks, we follow these main steps. Now again, these are not complete steps, there are more to it, but overall we can start with these 4 steps, right? So let's assume that we are focusing on a data set which is openly available in most of these frameworks. So let's assume we are using the MNIST dataset, right? So MNIST dataset is essentially, it has photos of digits from 0 to 9, and the class and the task for us is classification. So the task is classification, where we try to take in images, pass it through the CNN model, and it has to classify what is the class. So from 0 to 9, it just needs to give a class, right? Now once we have the data set, we will take the data set and split it into 2 parts, or essentially we would split it into 3 parts. So we would have a train set, we would have a val set, and we would have a test set. Now in standard data sets, this is well defined, right? Because a lot of researchers and students and developers would be working in the community. So you can't have different train, test and val split. So for standard data sets, yes, these splits are well defined. A common approach is take the train set, break it into 80%, 20% of the data set, and then try to define your test, train and val sets, right? And again, we'll in later lectures go into why this may not be the most optimal way. But for now, let's focus on this. So let's say that we have a data set that's openly available and that is part of the framework and that's widely used. We would have these sets for training, test and val, and we try to operate with all of them. Now essentially when you are working on a framework with a well defined data set, these splits are there, right? So the data loader actually does it for us. Now what is a data loader is something we'll see in the next tutorial, which is a breakdown of all these 4 steps in detail. However, for now, let's just say that we want to load the data set. It is a open, it's a benchmarking data set and it's had this many splits. The second part is the model definition, which is what model are we using? So what is the backbone that we are using? What is the model definition that we are using? Now again, if we are using standard CNN backbones, essentially those would be available in the particular framework. So let's say we have MATLAB, we can just ask or load AlexNet from MATLAB and the model would be loaded, right? And similarly it goes for even PyTorch and other frameworks. So when we are working with model definition, we would want to focus, at least for this example, on AlexNet, and this is also defined in the model itself. So we don't have to sit down and code for it from scratch, right? We can just directly use it from MATLAB. Okay. Now once we have defined this, we would want to essentially train the model. When we are training the model, this is taking into consideration all the things we have studied till now. So we are defining the input size of the model. Essentially, what is the input that the model would take? We would take in training strategies, which is the batch size, right, which would be the iterations, it would be the epochs, it would be the learning rate, right? All of those things which we have studied until now would be taken into consideration, and then we would start our training. Once the model is okay, now when we are training, our goal is similar to what we have been doing all along, which is essentially get the optimal parameters theta star, which is the arg minimum of the error. Let's define error as E theta. So essentially the goal for any training procedure is to get theta star. Now once we get the theta star, then we will go towards the inference stage, where we would just use this theta star, use the test set, and then pass it through the model. Once we pass it through the model, we will get some certain output y cap, and we would calculate our accuracy based on y cap and y, which is the ground truth, right? So these are the steps that even we will explore in the MATLAB, and these are overall the main parts when we are saying we want to train a neural network, right? These are the 4 main steps that we should take into consideration, and we would go into each of these steps in detail when we are going into the PyTorch tutorial, which is essentially what happens when we don't have a open source, or we don't have a standard data set. If I want to write a custom data set, how do we do it? How do we write data loaders? What is data augmentation? All of this we will keep it for the next tutorial. So essentially the goal is for us to see how the model is defined and are these steps being followed, and then during training, how is the training loss, how is the val loss, how is the test loss, right? As of now, this is our focus for this tutorial. A deeper dive is something we will push it for the next tutorial. Okay. Okay, so let's start with the mathematics behind deep learning for image recognition. So let's start with the fundamental component of CNN, which is the convolution operation, right? CNNs rely on the concept of convolution operation, which is a fundamental operation in signal processing. Convolution operation is essentially defined as follows. Convolution. So the convolution of 2 continuous signals is another signal. The value at some time t is defined as the integral of the products of the 2 signals, where one of the signal has been shifted by a time t. This is essentially what is observed in this given equation, right? Now let's take a demo and see what does convolution operation mean, right? So we have ut and vt, which are essentially the blue and red line, and these are the inputs. The green is the output that we get, wt, which is the output from the convolution operation. Let's just see how the demo looks like. So essentially when there is no overlap, the product is 0, so there is no output. But when there is an overlap, we can see that the convolution operation produces wt, which is essentially given by this function, right? So this is an operation between 2 signals, and it is a very fundamental operation in signal processing. Now let's also try to understand the interpretation of images and what does it mean when we are doing image based operation, right? So what we'll do is we'll take 2 images, right? So let's take images and then let's take images and then see their operation when we are doing it in the terms of a matrix, right? So we have 2 images here, which are grayscale images. The values range from 0 to 255. Essentially this MATLAB operation, this command is used to load these two images. So this is a giraffe and rhino that we see here, right? Now let's perform different operations. So because essentially these are two matrices, right? Now the images, once they are loaded into the variables G and R, they are essentially two matrices. Now when we do an addition operation which is adding two matrices, we get the figure on the right, which is an overlap of giraffe and rhino. Essentially all the pixels are being added element wise, right? Now let's compute the operation of 255 minus R. 255 minus R as observed gives us a value like this. Now let's multiply G and R. So we have the giraffe and rhino matrices. Let's do a multiplication. It results into something like this, which is not something we can directly interpret. Okay. And lastly, let's do an element wise multiplication. If we do an element wise multiplication, it gives us an image like this, right? Okay. Now let's take a simple example of a deep learning network and use it for the task of classification. Now as discussed in the previous slide or in the starting of the lecture, we want to load the image data, we want to define our network architecture, we want to specify the training, and essentially once we have specified and initialized, we want to train the whole model. Once we train the whole model, we want to see its prediction on the test set or on the newer data, right? So let's load and see what are the images. The images that are loaded here, this is how the images look like. So they are essentially just digits, right? Because it takes from MATLAB, which is the digit data set. Now let's also see the number of images in each category, right? And hence MATLAB has this command which is label count, and what we are trying to do is for each labels, what are the number of samples present. So for label 0, the number of samples are 1000, all the way till label 9 where the number of samples are again 1000, right? The dimension of this particular images or all the images in this data sets are 28 cross 28, right? Now let's define the training and the validation sets, right? Once we have defined the train and the val set, let's define the model architecture. Now we are essentially defining the CNN architecture, which is given from this particular piece of code. Again, in case we don't go into detail now, we will go into detail once we are looking at the PyTorch code, right? So we define all the layers, which is it starts with the input layer followed by convolution, batch norm, ReLU, right? Now in convolution layer, the input channels is 3, the output channels are 8. Sorry. In convolution layer, the 3 means the 3 cross 3 kernel, right? And we have padding which is same. Now one point that we want to observe here is generally whenever we are looking at convolution, batch norm and ReLU, they always operate in this order, which is CBR. So convolution, batch norm, ReLU, and then we can have a max pooling operation, and then again it repeats. So this is something we'll keep in mind when we are even looking at sophisticated architectures. Okay. Finally, once these layers are obtained, which is a set of, after passing it through a set of convolution layers, we'll essentially pass it through a linear layer and pass it through a softmax layer, finally getting the output predictions. Now these are some of the parameters that are used to define before we start the training, right? And these are all the terms that we are already accustomed with. We know it is the stochastic gradient descent, we know the learning rate, we know the maximum epochs, we know shuffle, we know what is the validation data, right? Now essentially when we train the whole model, we get a plot like this. Now I'm not running it now because it will take its time to plot this graph. Essentially, if we see the loss, we can see that the train loss consistently decreases, right? And corresponding to that, even the val loss decreases. So it's a very smooth curve, and overall we can see that the accuracy also keeps increasing as we train it for n epochs, or in this case it is around 4 to 5 epochs, right? Lastly, let's take an example of transfer learning using AlexNet. Now, transfer learning is essentially a way to fine tune the pre-trained AlexNet CNN to perform classification on a new set of images, right? AlexNet has already been pre-trained on ImageNet dataset, which has about 1000 object categories, and these are all general purpose categories. So it's keyboard, coffee, mug, pencil, and different types of animals, right? So the network has already learned a lot of useful features from these classes. Transfer learning is essentially we are taking the pre-trained network and trying to use it as the initialized network before as the starting point for the new task. So in transfer learning, we essentially take the pre-trained network and use it as the starting point for the newer task. Fine tuning is essentially not starting from scratch, but we are taking some knowledge of some previous data set while we are fine tuning the model. Okay. Now again, similar to what we saw earlier, the procedure while training the network remains the same. So we load the data set, we define the pre-trained network, we define the model, and in case the model is built up upon pre-trained network, we will load the pre-trained network. Finally, when we are training, we would go over certain training operations. Data augmentation is something we'll go in detail in the next tutorial, right? Then once we have trained the model, we would store the optimal weights, which is theta star, and then use it and then evaluate it on the validation set. Now this is the loading operation of the different images. Now the images that it uses is from the merge data, right? So this is what the data set looks like. So the number of classes here are about 5, right? And these are some of the randomly sampled images. We can see that these are not the images that may be present in ImageNet dataset. These are some different images from a different dataset, right? Now we load the pre-trained model. Once we load the pre-trained model, essentially we can also specify, or we can also see what was the size of the AlexNet, because that has to be the same size of this input, right? Now we can replace the final layers of this network. So we can extract the information from the pre-trained network, which is essentially the convolution or the CBR blocks, and also maybe some fully connected layers, but the last fully connected layer needs to be reinitialized. Why is that? It is because the new data set, so the previous data set where AlexNet was trained had 1000 classes. This data set has only, let's say, about 5 classes. Hence the final layer has to be modified. Okay, once this is done, we train the whole model. We will skip the augmentation for now because this is something we'll go over in detail. These are some of the training operations, or these are some of the training parameters that are initialized. Once we train, we can actually see the curve on the right. The graph here is not as smooth as the previous graph, and that is actually basically because the previous graph that we saw was trained on MNIST dataset, which is a much simpler dataset. Compared to that, training on this dataset is slightly harder, and this is essentially also how the training looks like. It's actually a very noisy process. It's not as smooth as we observed in the last time, right? So we can see that the training accuracy does fluctuate a lot. We can see that the loss is also fluctuating a lot. This is especially the training loss, right? And hence this is how we this is how the model is trained. Once the model is trained, we can classify it for validation images, which is essentially we can pass it to these, we can pass these images to the fine-tuned model, and we can get corresponding class labels. So to summarize, we saw what it means when we are doing convolution operation between 1D signals and its interpretation even for the images, right? And finally we went through a brief overview of how a neural network would be trained, which is the 4 main steps, which we would look into much more detail in the subsequent tutorial. This is mostly it could be a teaser to the whole operation that we do while we are training the neural network. And we looked at the approach of transfer learning, where we have a pre-trained pre-trained network. What we are trying to do is essentially we are trying to borrow the knowledge from a previous data set while we are fine tuning on the current data set, right? And it also is done basically to satisfy the heuristic that if the number of classes change, then the fully connected layer needs to be updated, right? Thank you.